Welcome, everybody. Please sit down. My name is Jens Pausberg. Today, we are going to hear from all the 13 Amazon Fellows. 2 years ago, Amazon and UCLA started the Science Hub for Humanity and Artificial Intelligence. And one of the things we do in the Science Hub is to fund Amazon Fellows, their PhD students, who are doing very well. And today they will talk about their research. And one of the people who is I would say the one who really is the person behind it all is Stefano, and here he is.
Not really, it's Jens, but thank you. Thank you, Jens, and thank you all for being here. It's very exciting. We really look forward to hearing from the fellows. And so I won't steal any time from all of them. So if you want to, please start lining up. And I guess, do we ask questions after each presentation? We wait until the end to ask questions.
So what we do is that we ask a couple of questions while the next person is setting up.
Okay, so thank you all for coming. Welcome. Congratulations to the fellows, and we can start with the first one. Thank you.
Very good. Sano, come up. So Sano Amini is the first speaker, and she will speak about reinforcement learning. And I think you have to speak into this microphone, but you should also speak loud because there's no, you cannot really hear yourself. So
Okay.
Anyway, so
Yep.
please.
Hi, everyone. Thank you for taking the time to be here. My name is Sana, and I'm a PhD student at the Electrical and Computer Engineering Department. And my advisor is Professor Lin Yang. I'm going to give a brief talk on my research on the applications of reinforcement learning and bandit methods in safety critical and multi-agent and lifelong learning systems. Let me start with a brief background on the definition of a multi-bandit problem and a reinforcement learning problem. So let's start with the common aspect of these two problems. So they both involve a learning agent that interacts with an unknown environment by repeatedly playing actions and receiving some reward or cost from this unknown environment. And the goal is always to maximize this notion of reward. The difference between these two learning frameworks is that multi-bandit is basically a single-stage interactive learning framework, and reinforcement learning is a multi-stage interactive learning framework. I'm going to elaborate a bit further here. So a multi-bandit problem involves an action set, a reward function which is unknown, and this reward function is only a function of the action that you play, the agent or the learner plays. And the goal is to learn the optimal action by receiving feedback from the environment. And the challenge is that this reward is unknown because the environment is unknown. So we need to come up with like efficient solutions. But in reinforcement learning, we face multiple stages in the learning process. So this multi-stage interactive framework is usually modeled through a Markov decision process, which involves a state set, an action set, and here H is the horizon or the number of stages, and a transition kernel and a reward function. So the transition kernel basically means tells you what's the probability of transitioning to state S prime when you are currently at state S and you are playing action A at this state. And then the reward here is a function of state and action, but in a bandit framework, the reward was only a function of action. So the action that you play at state S gives you a different reward from what you're given as a reward in state S prime by playing the same action. So here H is the number of stages and is greater than 1, and a policy is defined to be a function that maps the state set to some distribution over the action set. And the goal is to find the optimal policy that maximizes the expected cumulative reward. So here the reward, what we want to maximize is this accumulation of rewards over these H stages. Yeah, so these are the learning frameworks that I've been using in my research, but the applications that I was focusing on, the first one is the application of safety critical systems like self-driving cars, medical trials. And by safety critical systems, I basically mean that the learner not only wants to maximize some notion of reward, not only wants to have the best performance, but also wants to make sure that it is only playing some safe policies, because there are certain policies playing which may result in catastrophic results, like in self-driving cars or medical trials. So the goal is twofold here. We want to maximize the reward, and we want to make sure that the safety requirements are satisfied. But again, the challenge is that these safety requirements are typically unknown. So that adds to the challenge of maximizing the reward. The second application is the application of multi-agent systems or distributed systems, where we have a bunch of learners or agents that are trying to help each other to achieve the common goal of maximizing the reward in the same environment. So they can move towards the optimal policy or optimal action faster individually. And it's, sorry, I have one more slide, and it's the third application is on lifelong learning, where the agent's goal is to find a multi-task policy, which basically means that we are facing, the agent is facing a bunch of tasks that are arriving in a streaming sequence, and they're related to each other. So when you're receiving one task, you want to use the information that you received from previous tasks to help to learn the optimal policy for the current task faster. And we're trying to propose computationally efficient solutions for these specific systems. And thank you.
Next speaker come up, but questions while we're setting up for the next one. Questions, anyone? Don't be shy. You can ask a question. Yeah.
You expand more on what you were talking about with not letting the road run about violating safety constraints. You were saying that it's possible you might not know whether there's constraints are ahead of time. So
Yeah.
what are some avenues possibly around that?
So one can possibly, so you can always, we hope that the agent can always be given at least one safe policy, which is not good, but it's known to be safe. So you can start with that and then receive some feedback as you like move forward. You can receive some feedback regarding this. But whenever you don't have anything to play, you have no knowledge about the safety requirement, you know that the system would have a given safe policy. So that's one assumption that we've always, I mean, I consider it important, but there are other ways, like people let some.
Okay. Okay, so now I cut you off, and then you have to hold the microphone right here. And then
I
you
see.
speak.
I see.
So don't hold it too close because then,
Okay.
it'll be too loud.
Okay.
Okay, so I just want to say the next speaker is Vivian Channing. I know her as Vivian, and she will talk about grappling.
Sure. Thank you for the introduction. I'm a PhD student who working with Professor Izhou Sun, and my research interesting is mainly focused on the knowledge graph reasoning task. So today I would like to introduce my research over the neurosymbolic reasoning for knowledge graph reasoning to everyone. As everyone already be familiar, knowledge graph is a multi-relational network which provide the collection of real-world facts to everyone, and then they provide many valuable resources for many real-world applications, such as the NLP task, the question answering system, and the product recommendation systems. Although they are very useful and then apply to many real world and have many successful application in many real world scenario, they are usually incomplete. So they're the fundamental task for knowledge graph reasoning is to predict the missing link by reasoning over the existing fact. The existing work for the knowledge graph reasoning can be broadly divided into two directions. The first direction is the traditional symbolic reasoning, and the other is the modern representation learning-based method. And then the earlier work is mainly represented by the traditional symbolic method. So the basic idea of the symbolic method is trying to leverage the logical rule, which is predefined by the human, to help us to conduct reasoning to infer the missing fact in the knowledge graph. And then the other direction, which is the modern representation learning-based method, is trying to learn representation for the to represent entity and the relation in the knowledge graph in order to infer the new fact. However, both methods have their own advantage and disadvantage. The symbolic methods are able to use the domain knowledge and which have a very good interpretability, but the neural methods are more efficient and then they have a better modeling capability. My research is mainly focused on, most of my research is focused on how to leverage the advantage of the both neural and the symbolic reasoning for knowledge graph reasoning. But one of the main challenge for the neurosymbolic reasoning method for knowledge graph reasoning is that they require some logical root to be predefined by human being in order to specify the domain knowledge and inject domain knowledge. But the logical rule are usually need to be specified by the human being, and that is label intensive. In order to reduce the demands on the human effort, next, I would like to introduce our recent work on the logical rule learning. And then the goal of this work is to learn the logical rule given the knowledge graph without the involve of any human effort. And then the idea is like we would like to learn the goal as shown. We would like to learn the rule as shown in the slides, and then each rule will be associated with a confidence score indicating how likely the rule holds true. As shown in the example in the slides, we can see that usually this is how knowledge graph looks like, and then we can see that we might observe some instance rule from the knowledge graph. But the thing is like now our goal is to learn some template rule, which will involve those like variable things. And then how to bridge the gap between the instance level observation and schema level abstraction is the main challenge for the rule learning. And then all the previous works trying to evaluate the plausibility of logical rule by counting the observed rule instance. So the idea is like enumerate the rule instance, but that could be super computational expensive. Therefore, they usually have limits scalability to knowledge graph size. And then they could not be reliable because sometimes we will missing some fact from the knowledge graph, and then without the fully observed fact in the knowledge graph, or we might not be able to learn some logical rules.
Are you also almost up against?
Yeah, so yeah, I would like to do this quickly, and then another thing is like a logical rule have like deductive nature. So usually when we're trying to do the logical, if I require you to infer the head of this rule body, usually we will trying to split the whole process into small steps. And then we can infer the final conclusion step by step, but the current method cannot cannot following this deductive nature to infer rules. So basically what we trying to propose is like we would like to propose a representation learning based method to learn this logical rule, and then essentially we also like propose a method to push this deductive reasoning into the rule learning smartly in order to require all the learned rule following this deductive nature. And then that is like the overall framework of the whole framework. And then the rule learning is like a rising area, and then for the future work of this work, we would like to extend this logical rule mining from the knowledge graph to some unstructured natural language, which is trying to mine the rule from some unstructured text. Yeah.
Thank you. I think we have to skip the questions. I'm a realist, so we will skip questions from now on. But next speaker, please come up. The next speaker is C.E. Zhou, and he's going to talk about, I guess, connecting language to perception and action. And over to you.
Thank you.
So you hold the microphone up. So like this is the microphone, this little thing.
Oh, okay.
And then, yeah, try that.
Okay. Okay. So yeah, hi everyone. So my name is Z, and I'm a PhD student working with Navin Vadapong. So today I'm going to talk about my research on pre-training end-to-end vision language transformers. So my research is focused on vision and language tasks. So for vision and language models, they try to combine information from both the vision and the text modalities, and then they can perform various tasks like video question answering. So for example, in video question answering, the model is given an image and a natural language question about this image, and it is required to understand both the image input and the text input in order to provide an answer. And in this direction, most people would use pre-training. So they would first pre-train the vision language model on a large image calculation corpus, and then fine-tune the pre-trained model on some specific tasks. And most of the previous work in this direction use pre-trained object detectors to extract vision features. So specifically, they would use a pre-trained object detector to first extract the regions as well as their region features from an image, and then they will feed these regions and region features to some cross-model interaction modules like a transformer. So this kind of approach can have several drawbacks. For example, the region extraction part can be very time consuming, and also because the object detector is usually frozen during pre-training, so this can limit the capacity of the whole model. And on the other hand, transformers have shown promising performance in both natural language processing and computer vision. This means that we can potentially have a unified architecture for both the vision and language modalities. And also because now that we can use vision transformers to extract vision features from an image and then feed the vision features to some cross-model to like a transformer module, then this means that we can train the whole module, train both the cross-model module and the unimodal module in an end-to-end manner. So based on this motivation, we investigate how we can pre-train vision language transformers. So we present these framework called Meter. So in this framework, we identify several important modules of a vision and language transformer. For example, we investigated which vision encoder we should use, which text encoder we should use, and how we can aggregate the features from different modalities and the model architecture, like whether we should use an encoder-only architecture or an encoder-decoder architecture, and also how should which pre-training objectives we should use for pre-training. We did these empirical studies, and we find out the optimal configuration on each of the modules. And in the end, we can obtain a strong vision language transformer that can obtain SOLID performance across tasks. So in the previous CVPR paper, we are mainly focused on image level tasks such as video question answering, image captioning, and image text retrieval. But in addition to these kind of tasks, we also have other region level tasks like object detection and phrase grounding. So for these tasks, the model is required to output some fine-grained predictions. For example, for the task of phrase grounding, the model is given an image and an image caption, and the model needs to ground each natural language phrase in this caption to its corresponding image region in this input image. So this requires the model to output some specific bounding boxes for a given input. So the model needs to output this fine-grained information, but to train such models is hard and costly to collect these fine-grained annotations. So in order to solve this issue, we propose these in our newest paper. We propose these cost-defined pre-training paradigm that can support both image level and region level tasks. So the first, so we have this cost-defined pre-training paradigm, where in the first stage of pre-training, we would pre-train the models on large image caption data as before. So this step is scalable because we can easily scrape millions or even billions of image caption data online, and then we can pre-train the model with objectives such as mask control modeling, image task matching, etc. The pre-trained model can then be fine-tuned for these image level tasks. And after this first stage is done, we can then do further pre-training like this image caption data, as well as the alignment information between natural language phrases and the bounding boxes. And although this step is not that scalable, but we have this, since we have these strong initialization point from the first stage pre-training, the model is start off strong, and then we can do some simple further pre-training, and then the pre-trained model can be adapted to tasks such as object detection and phrase grounding. So and then in addition to the region level task, we also have even more fine-grained tasks like pixel level tasks like segmentation. And so in our recent work, we also propose another model called XDecoder that can support both these pixel level tasks and vision language tasks. So yeah, to conclude, my research is focused on building vision language models for tasks of different granularities. Yeah, thank you.
Okay, next speaker, Kai Takami.
Yes.
I'm pretty sure it's going to be about turbulent flow analysis.
Yes, exactly. Oh, it's my last slide. Oh my god.
I've learned.
You've learned.
Okay.
Hey, so hello everyone. This is Kai Takami from the Department of Mechanical and Aerospace Engineering. My major is fluid mechanics, which is discipline to study the flow around us, including the water and the air. So my talk will be a bit different flavor of from the other speakers, but I'd be happy if you can enjoy my talk. Okay, I have to do anyway. Especially today, I'm going to focus on developing artificial intelligence-based techniques for turbulent flow analysis, which is very, very chaotic, and the strong nonlinearity is having, like, as you can see here. Especially today, I'm going to focus on reconstructing flow from the limited sensor measurement, which is very, very important for us from the aspect of the controlling and understanding the flows. So here, let's consider the flow, let's say, on the airplane. So now you're on the airplane, then now the particular interest here is how you can reduce the resistance around airplane so-called drag so that you can smoothly move to your destination. In the scenario, you have to control something around us. Then in order to develop a control strategy, what you have to do first is knowing around us or knowing what's going on around the flows. In that scenario, knowing or reconstructing flow from the sparse sensor measurement on the airport surface or airplane surface is very important. Now, our idea here is whether we can leverage data science and machine learning techniques to gain the situational awareness from the limited measurements. We're doing this from the aspect of the super resolution analysis, which you may know to reconstruct the high resolution signal from low resolution its counterpart originally developed in image science. In recent years, we have been working on this machine learning based super resolution analysis for vertical flows. So for example, here, let's take an example of two-dimensional homogeneous tropic turbulence, which is a, let's say, canonical flow example in engineering applications. So first we take the two cos spatial low resolution image, then we can reconstruct the high resolution data using machine learning FX. Then now, in addition to the spatial reconstruction, actually, we are also interested in the temporal data reconstruction, so-called in-betweening. In-betweening is a concept to non-linearly interpret the video sequences from only the first and the end of the snapshot. The reason why you can be happy here is that because you're able to reconstruct the time series from only the first and end of snapshot with machine learning. You don't need to save all snapshot, which would be useful for data saving or data storage mitigation. How? For FX and FT, we use the neural network. Here, let me skip the details, but if you are interested, please refer to these papers. You can go over my name so that you can find my papers. But here, let me note that special care is needed because our data is governed by strong nonlinearity. So in order to account for the multi-scale nature, strong nonlinearity, you have to care the construction of neural networks. The reason why now we are actually very excited with this super resolution idea is actually super resolution can be a general framework for a broad range of applications in fluid mechanics. For example, let's back to the sparse sensor reconstruction problem. If you consider a set of the sparse sensor measurement as a low resolution data, actually sparse sensor reconstruction problem can be replaced with super resolution analysis. You may be able to consider noisy flow fields which can be measured in the experiment. This can be replaced with low resolution data. And as I said, now temporal reconstruction, so-called in-betweening, can also be replaced with super resolution analysis. We have recently surveyed the recent study and trend of machine learning-based super resolution analysis for fluid flows. So if you are interested about the super resolution and fluid mechanics, please visit our paper too. Now, what we are doing is, our idea is whether we can apply our fundamental idea for more practical and turbulent chaotic flows around, let's say, industrial fluid-based machines or airplanes. What I'm showing here is, left one is now, I'm showing the fluid control, the really huge system that can control the amount of the water using the PAMSEM. And the right one is, as you can see, it's a flow on the airplane. Then actually we have recently also developed a method to reconstruct the vertical structure on the PAMSEM from the sensor measurement. Yeah, so with that, let me conclude my presentation. And we are currently being very, very excited with the potential of data science or artificial intelligence-based techniques for fluid mechanics. I'd be happy to take any questions. Thanks.
Okay, next speaker. Well, yeah, we don't really have time for questions. I wanted to keep it. But here's Boucher Hua. He is coming up. And let's see. Computational and microscopy stuff.
You can see the presenter's nose.
Microscopy and
Can you get the presenter's? You should go to slideshow and select
I knew ChatGPT would show up at a slide at some point. Okay, please.
Okay, yeah. Thank you very much, Kai. That's very fantastic talk in physics. And now let's look at another aspect in physics, which is microscopy imaging. As you know, microscopy is a very important technique in human history to discover some miniature structures of biological samples. And I'm Lu Zhe from ECE department, and today I'm going to share some of our recent research on self-supervised learning in computational microscopy. So to understand what is self-supervised learning, we need to think about common sense first. Common sense is generalized knowledge of humans and animals that forms the bulk of knowledge in our fields. If we, for example, if we show some fruits to an infant, even if the infant has never known these fruits, the kind of fruits, the name of fruits before, after sufficient learning, he can distinguish like what is apple or what is orange, even though he does not know the name of these kinds of fruits. So that is common sense. Every person is naturally granted this ability to tell apart different objects of different classes. However, this natural ability is still an open challenge to artificial intelligence, as the AI cannot efficiently learn without a supervised label. A recent breakthrough in large language model is ChatGPT. As we know, it uses self-supervised generative pre-training, and it turns out that this model surpasses all previous NLP models in some downstream tasks. And we wonder why we need self-supervised learning in microscope imaging. In the past decades, we have seen deep learning methods to surpass traditional algorithms in in microscopic imaging. For example, like phase imaging, super resolution of images, and image denoising. However, most of these methods are supervised, which intrinsically have three major limitations. The first is generalizability. Supervised learning needs massive label dataset, and often we need transfer learning to apply a trained network to a new type of sample. The second limitation is supervised learning needs labeled experimental data. And in microscope imaging, it's not easy to capture a very large dataset, as it will include huge costs and labor. Besides, incorrect labeling may introduce bias to the trained model. And third thing is the interpretation. As we are doing a physical scene, so it's important to incorporate the physical knowledge in this field with our model, while the conventional deep learning models lack this relation to the physical laws. So we ask ourselves, how can we apply the idea of self-supervised learning to our research? The answer is here. We focus on the inverse problems in computational microscopy. The inverse problem aims to solve the high-dimensional target information. Here we denote it as O from a low-resolution or low-dimensional measurement, I. And here I'm showing the paradigm of conventional algorithms and experimental data-driven supervised training. Instead of directly train the network by comparing the outputs and the ground truths, we use the knowledge about the physical forward process, and we propagate the output, the network output, to the measurement domain again. And then we compare the actual measurement and our predicted measurement. And this forms the loss, and we can do back propagation. To validate our idea, we test it on a computational microscopy task called holographic imaging. And to furthermore eliminate our requirement for experimental data, this time we choose some artificial random image as the training data. So firstly, we train our network on simulated holograms generated from random artificial images, and then directly tested on experimental holograms. As you can see, the trained model can successfully generalize to experimental data of tissue samples. So to conclude, our method is promising in solving many challenges in computational microscope imaging, and also is potentially to other computational imaging tasks and CV tasks. Thank you very much.
Thank you. Very good. Alexander Johnson, come on. You are going to talk about automatic speech recognition, yes?
Yeah.
Okay, here you go. So just the little thing there, that's the microphone. You don't have to hold it very close because it seems to be quite powerful.
Hey, what's good? My name is AJ and I'm a grad student in electrical engineering here, advised by Professor Alwan. And I'm gonna talk about inclusive automatic assessments of children's oral language development. So oral language assessments are an integral part of early education for children in case a child might be falling behind in their grade level, if they're not reading at an appropriate level, if they may have some type of speech disability that may need intervention. Oral language assessments are one of the primary ways teachers and clinicians are trained to look for those early. And in our work, we're currently focusing on these kind of oral language assessments for speakers of African American English. So to give an example of one of these oral language assessments, we might have a scene from a rainy day like today, and we have the teacher ask the student, please describe this picture as completely as you can. So some responses from the kid might be, that boy, he ain't got no umbrella. Those kids taking their time walking across the street. She had asked her mom, take her home, much smarter than me, getting wet today. So we might notice in these sentences that there are some differences between this and the standard American English you might hear on the news every day. So a clinician or a teacher needs to be aware of which type of speech differences indicate that this child needs intervention from a speech language pathologist or a language expert, and what kind of speech differences are a normal sign of healthy development within a dialect that is just different than the standard American English. And in our work, we're seeing if we can train a machine to do this. There are several challenges in doing this. First of all, there's a lack of in-domain training data. I don't know if you guys have ever tried to get a kid to sit down and record them for 15 minutes, but it is difficult. So there's not a ton of data to learn this from. There's a lot of variability in children's speech as they grow and develop at different rates. They may not all talk the same way, and a machine has to learn to deal with those differences. And there's variability across and within dialects, with examples like code switching, switching between two dialects. In our work, what we focus on is creating a pipeline for this kind of assessment. In this proposal, we have the input, which then goes through a system trained to do dialect identification. That system will then predict in what dialect the user is currently speaking, and then choose an appropriate acoustic model for that speaker. This acoustic model will then pass the output transcript to a natural language processing model, which will get from the transcripts their prediction of how well the child did on the assessment. First, in our work, we have a model for dialect identification. In this work, we have several acoustic features which were extracted from the speech, including features for phonetic modeling taken from self-supervised learning representations. We have speaker identification features, paralinguistic features, and other representations of how the speaker might have sounded. We then train a model to be able to predict the output dialect and the strength of the dialect or dialect density from the input speech. In this work, we use XGBoost as our model because it gives us the power to not only predict with high accuracy, but also to explain which features were used and how often they were used in prediction for transparent and explainable AI. The next step in this pipeline is to fine-tune automatic speech recognition models to be able to complete a fair assessment of the child's language abilities. We choose an acoustic and language model that are fit to the target dialect. In this work, we completed a data augmentation strategy called LPC Augment, in which we shifted the formant frequencies of the input speech to values that might be expected in Southern African American English from kids from the California area in order to create more artificial training data to create a more inclusive ASR model. and then given output transcripts that are best matched to the target speaker, we then perform natural language processing downstream tasks on them, like semantic similarity scores with the target prompts that the kid was trying to be elicited to read, recall of the keywords from the assessment, how well they were able to match the verb tense to the original prompt given by the teacher, and other categories in assessment to see how well the child can do. Then a classifier will give the appropriate score. And from this, we aim to train a classifier to give a fair diagnostic in the child's dialect. Thank you.
Very good. Thank you very much. I feel pretty sure you're going to talk about uncertainty and decision making and that kind of thing. Am I right?
Not really.
Not really?
Yeah, I want to talk about climate change and
You will?
Yeah.
All right, great. Always good to be positively surprised. So thank you. Over to you.
okay. Hi everyone. My name is Tung Nguyen. I'm a second-year PhD student in computer science, advised by Professor Aditya Grover. And my current research focuses on building foundation models for weather and climate modeling. So as you may already know, climate change is one of the most important problems that we have to tackle in the 21st century. So we see that the extreme events are happening at an increasing pace and are becoming more and more damaging. So given this, it is very important that we can reliably and accurately model the climate and model the weather. So the current approach to weather modeling and climate modeling is based on numerical methods where we employ explicit equations that are based on the laws of physics, fluid motion, and chemistry. So these models have been developed by climate scientists for so many years, and they are reasonably accurate because we encode a lot of knowledge about the Earth, and they are also very general purpose in the sense that one system of equations can be used to do so many different tasks, from weather forecasting to climate projections. However, these models are also very well known to be super slow and computationally expensive. So an alternative approach to weather and climate modeling is data-driven. So basically, the main idea here is that given a historical data set, we can train a deep neural network on this data in order to solve a certain task, for example, predicting the weather the next 3 or 5 days. And these models can actually achieve a competitive accuracies and can make much faster predictions compared to the numerical methods. However, as we may already know, deep learning is very data hungry, and one model can only perform a certain task that was pre-trained or it was changed to perform. So in order to solve these two issues, we propose the idea of building foundation models. So the idea is actually inspired from the fields of language and vision. So previously, many years ago, when we want to learn a model that can perform a certain task, we have to first collect the data for that particular task and then train a model to perform that task. However, what we do today is we first collect a huge data collection, and then we pre-train the model, pre-train a huge model. And then if we want to adapt to a new task, a test time, we can either fine-tune the model, or we can even do zero-shot learning, so there's no fine-tuning involved. So we want to apply that idea into the field of climate and weather modeling. The main reason behind that is we see a lot of opportunities. So there is plenty of data that we can use to pre-train the model. The data can come from weather stations, can come from ships, can come from airplanes and weather balloons to collect data up in the air. We can also have data from satellite data. We also have simulated data, which is not real, but also but can also provide important information to learn from. And there's a very fun fact that ECMWF, which is the biggest organization in climate science in Europe, they receive more than 800 million observations every day. So that is a lot of data to learn from. However, opportunities also come with a lot of challenges. So these data sources, they actually are very diverse and have different and are very different in nature. They can have different temporal coverages. So one data set can be collected in a certain period. They can cover different spatial locations. So maybe one data set is global data, but the other data set only contains data in North America. They also have different underlying variables. So maybe one data set can have temperature, the other data set doesn't. If they are simulated data sets, they can have different modeling assumptions and measurement methods. So recently we proposed a new method that can be pre-trained on a lot of different data sources. So that is one property of this model. And after pre-training, the model can be fine-tuned to perform so many different climate and weather tasks. For example, it can make predictions for the weather from only a few hours ahead until few weeks or even few months ahead. It can make predictions for global data or local data. And it can also perform climate projections and climate downscaling. Even though this is a very promising work, I think there are many directions that we can also explore. We can scale up the model with respect to the pre-training data size and the model size. We can make the model more general to more downstream tasks. We can have a better architecture or a better pre-training objective. And even better, we can do something like GPT-3 style for weather and climate, where there's no need for fine-tuning. We just input the new data and the model can make like in-context learning directly without any fine-tuning. So that's everything I wanted to say. Thank you for listening.
Thank you very much. Okay, Alexander Schwaber, come on. So now my track record has gotten a hit, but you're going to talk about robots, yes?
Yes.
Okay,
exactly.
So safe robots.
Hopefully.
Hopefully safe.
We'll see.
Okay, all right.
All right, so my name is Alex. I'll be presenting on autonomous locomotion and manipulation of robotic systems. So robots are supposed to be autonomous, but to fulfill this requirement is very challenging because they must constantly adapt and also learn on their own. So my interest is really in how to use planning, vision, mapping, controls, estimation, all simultaneously within an end-to-end framework for autonomous behavior. So the first work in this direction is called risk-averse MPC via visual inertial input and recurrent networks for online collision avoidance. So in this work, I used an MPC for high-level online path planning, which was informed on an object detection system and an RNN. This RNN was trained on SLAM post estimations. So essentially what the RNN does is able to predict and propagate uncertainty covariances. So this is just a visual demonstration of the SLAM algorithm that we use. So the whole point of having an idea of uncertainty is that you can do much better obstacle avoidance. So for instance, you can do safe and also fast obstacle avoidance if you actually understand how the uncertainty dynamically is propagated, which is better than a naive approach where just inflating your sort of uncertainty to some constant value. Then it might be safe, but very slow obstacle avoidance. So here I show a more complicated example of giving it 3 goal points, and then it just autonomously goes to these points. So I expanded this work into the next one for multi-agent planning. So I still use the same idea of the RNN, but again, now I use a drone and a turtle bot to do a very similar concept for obstacle avoidance. And then more recently, I was focused on doing auto-tuning of control and online trajectory planner for legged robots. So this is something I presented in Kyoto at IROS. The idea of this work is that I had a planner that creates these reference trajectories and also a controller that consisted of 2 different controllers. So when a leg is in stance, I use an MPC stance controller. In swing, I use a PD controller. And what tied everything together is this auto-tuning formula, which consists of an unscented Kalman filter that would essentially automatically tune both of these controllers. And not only that, but also the reference trajectory directly. I expanded this auto-tuning approach to do like some real-to-sim work as well. So in this work, I essentially tried to learn the residual error between the simulator and the real robot. And then I also use this approach to do better force control. So specifically, I used an admittance controller, which was then augmented by this auto-tuning approach for robotic climbing. So currently I'm working on 2 projects. So one is a planner for robotic free climbing using reinforcement learning. And the second is more of a state estimation project. So for robots to be not just autonomous, but also useful for diverse sets of tasks, I really believe we need to begin doing local manipulation. It's a big reason why, if you look at the trend of Boston Dynamics, they started with doing extremely good locomotion, but now they're attaching grippers to the robots and manipulator arms to do local manipulation. So a climbing robot is actually really the perfect platform to test this kind of local manipulation problem. This is why I plan to use Scalar. This is our climbing robot that can do vertical climbing and also ceiling climbing. But one thing that you might have noticed is that there's no onboard camera, so it's not creating these trajectories autonomously. These were pre-planned. So my plan is now to do it more autonomously. So to do that, we have, of course, the state estimation project. Here I plan to use a factor graph to do state fusion. And then the whole point of doing good state estimation is we can have a better idea of the map, which is really important for robotics or for climbing robots. So I know where all the bouldering holes are located. This is fed through a teacher-student RL policy for planning, which gives us these reference trajectories. And last, we can have a controller like MPC to track these trajectories. So for the next 3 months, my focus is really on the planner side. This includes building a climbing robot simulator from scratch. There's really nothing available, at least that considers physics. So that's something I've been working on the past few weeks. And then this is just a flow chart of all the teacher-student policy. The main idea here really is that I have privileged information and non-privileged information for the teacher policy, but the student policy only has the non-privileged information. So by privileged information, I really mean that it has an idea where all the bouldering holes are located, but for the student policy, it does not know. But it does have in the observation space the depth image and the whole idea of this is that from the depth image, it will understand where these bouldering holes are located as the student tries to mimic the teacher in this respect. Yeah, thanks for listening. Thank you very much.
Okay, Xiaoqing Shi, where are you? All right, I'm up. You'll talk about machine learning, right?
Yeah.
Yes. Trustworthy machine learning. Robust machine learning. Okay, over to you. Wow.
Hi everyone. My name. Hi everyone. So my name is machine learning, covering problems related to the evaluation, formal verification, and training for robust machine learning. The first problem is the evaluation on the robustness of machine learning models to distribution shifts when there are some difference between the training distribution and testing distribution. The evaluation itself is difficult because there are several reasons. Earlier works have been using synthetic distribution shifts to evaluate the robustness, but synthetic distributions cannot represent natural distribution shifts, and we may have very different observations. So some works have been constructing natural benchmarks to evaluate the robustness of the models on natural distribution shifts where the images are natural images that the wild. But another issue is that out of distribution performance evaluated on this benchmarks with distribution shifts is often strongly correlated with in-distribution performance. So it becomes unclear if a model with a higher out of distribution performance is effectively more robust, or if it's just because it has better in-distribution performance. So some works have been controlling for the performance on the in-distribution test set, which is typically ImageNet. But what if we have models trained on different data, especially nowadays we have many pre-trained models. So a kind of recent pre-trained models is called trip models. Several previous works have been using ImageNet as an in-distribution test set to compare different models. They find pre-trained trip models appear to be much more robust than standard image models. The trip models are on the upper purple line, and standard ImageNet models are on the lower blue line. But they are in ImageNet as an in-distribution test set, but trip models are never trained on ImageNet. So this is problematic. In our recent work, we have proposed to control for multiple the performance on multiple training distributions, multiple in-distribution test sets that cover the training distributions of all the models on the right image. So if we plot the out-of-distribution accuracy of all the models against multiple in-distribution accuracies, we find that all these models lie on a simple plane. So this means that none of these models, including pretend trip models, are effectively more robust than others, because all these models just have similar robustness that can be expected from in-distributed performance. So this is on the evaluation. I'm also working on neural network verification, where we want to verify the behavior of neural networks on a range of inputs. So typically people usually people evaluate machine learning models on a single instance at each time, but here we want to verify the behavior on a range of inputs, for example, a ball. And we want to verify the output range of the model given a range of inputs, and then we want the results to be provably correct and verifiable. So I'm working towards more general and efficient frameworks from early transformers and later on general computational graphs and higher order computational graphs. We are working towards solving some real world verification problems, and we also have a open source library for automatic verification given some PyTorch models. And lastly, I'm also working on training more robust neural networks. So if we have different kinds of perturbations on an image of dog, we want to see what is the worst case output given all possible perturbations. And we want to certify if the worst case output of the model will be provably correct. Will be provably correct against all possible perturbations, and we want this we want this evaluation to be provably verifiable. So that's all about my work. That's
Very good. Xiaoqian Wang, where are you? Thank you. I think it's the second microscopy talk of the day, yes? Yes. Very cool. I think this is going to be high speed microscopy. Kilohertz volume rate, that's as fast as it gets.
Yeah.
All right.
So hi everyone, my name is Xiaoqian and I'm from bioengineering department, and I'm going to present our recent work on high-speed 3D imaging. So fluorescent microscope is very important, as previously mentioned. And people try to make the microscope to see deeper, to see clearer, to see with great detail. And now we want to make it see faster. So the limitation of the speed comes from the hardware, comes from the bandwidth of the optoelectronic devices. So like the camera, like the scanner. So as a result, we can only read out a certain number of pixels for a given time. So intuitive thought will be, if we can make one measurement occupy less pixels, then we can make more measurement for this given time, so we can image faster. So we try to find an optic system that can compress the image into as few pixels as possible. And then in the post-processing, we can use the algorithm to reconstruct it, to restore the original high dimension data cube. And in our case, that high dimension data cube is a 3 data cube XYZ information. So we have performed the optic design for two main objectives. The first one is to use a combination of a spherical lens, dot prism, and a cylindrical lens to achieve optic image transformation. So we can compress a 2D image into a 1D projection, and we can read out one row pixel, and that contains all the information we need for the original 2D image. And the second objective is to fabricate everything in an array, so we can simultaneously capture multiple images, so we are able to simultaneously focus on different depths. So in a word, we can use the system to do 3D imaging from a snapshot and with much fewer pixel numbers. So we have implemented the system in the lab, we have built this, and in the optic testing, we can detect the signal from a field of view of 400 by 400 by 200 micrometers at 8,000 volts per second. So this is going to be the fastest fluorescent microscope ever reported in literature. So in the right corner, this is an example of the detection of the measurement in our camera. So this is nothing similar to the image you normally see in a fluorescent microscope, because everything is encoded, is compressed. So the final step is to find a way to decode it, to solve the problem, so we can reconstruct the original 3D information.
And the reconstruction in traditional algorithm can be written in such optimization problem. We know the form model of our image system A here. We know the measurement B here. So we try to find a solution X that satisfies this form model, as well as some image priors. Phi X here is a regularization term. So we can rewrite this problem into an iterative step. In the first step, we optimize X. It is a Euclidean projection, so we can write out the closed form solution. It is just to ensure the fidelity. And the second step is a classical denoising problem. We can use some TV denoiser or L1 norm denoiser based on the regularization you choose. And we iterate between these two steps to approximate the final solution X. And then in our method, we try to unfold everything. We try to unfold iteration and connect everything one by one. So we can replace some component with convolutional neural network and train everything in an end-to-end manner. So in each module here, for example, in the first module here, which represents the first iteration, it has two sub-steps. The first step is a projection. It's just the closed form solution here, which will add the form model constraint. And the second step is a denoiser. We can use a 2D UNet to replace the original denoiser. And we can train everything end-to-end on our experimentally acquired data pairs. So in this way, we are able to add an explicit image model, the physical model, to the learning-based method. With such system and algorithm, we are able to do imaging on biological samples. The first row shows the vasculature network of a zebrafish. This is the vessels of the brain. And the second row shows how we're going to image the neural activity of the zebrafish. So you see those sparkling signals, they are the neural activity of the zebrafish. So everything is performed at high speed, 3D, and in fluorescence. Thank you.
Yeah, come on. We're bringing all that up too. Okay. You will talk about machine learning, yes?
Yes.
Aha. Efficient deep learning. Okay.
Thank you.
You have this under control? All right.
Yes. Hello, everyone. I'm Yu Yang, second year PhD student from Computer Science Department, advised by Professor Bahram Mirza Suleiman. I'm delighted to share with you some project that I'm working on over the past year, aiming at enhancing the efficiency and robustness of deep learning on large data. In machine learning, algorithms act as engines while data serves as fuel. To keep up with the increasing size of models, visions and language datasets have undergone significant growth over the years, expanding by orders of magnitude. However, training on such huge datasets can be extremely costly. For example, the language model GPT-3 was trained with 45 terabytes of data. The energy consumed during GPT-3's training is equivalent to 17.8 times the average yearly energy consumption of an American. And the amount of CO2 emitted during the training is equivalent to driving a car from Earth to the moon and back. Not only training with large data set is expensive, but it can also be risky. Since much of this data is often crowded from the internet, it can be vulnerable to data poisoning attacks. In such attacks, imperceptible perturbations are made to public data, in this case, images of birds, to create what we call poisons. If a small set of these poisons is added to the training data, the trained model will incorrectly classify a target image as a bird during testing. Another issue with large real-world dataset is that they often have a bias towards the majority. As you can see on the right side of this slide, the minorities have far less training data compared to the majorities on the left. As a result, the model trained on this biased data will have a lower accuracy rate when tested on these underrepresented groups. My research addresses these problems by developing theoretically rigorous methods to improve efficiency and robustness of learning from large data. Our findings suggest that gradient information can be useful in addressing the above problems. By clustering the training examples based on their gradients, we can obtain valuable insights. This clustering problem is submodular, meaning it can be solved quickly using a greedy algorithm that ensures a nearly optimal solution. To tackle the first problem, our proposal involves using the centers and sizes of clusters to estimate their gradients. This helps to speed up the training process. Our proposed algorithm trains only the centers of the gradient clusters. By doing so, it is twice faster as training on the entire data set while still achieving similar accuracy. It is also the only algorithm that guarantees faster training times for larger data sets and models based on theoretical principles. To address the second problem, we improve the model's robustness against data poisoning attacks by removing size 1 clusters, which typically contain examples with outlier gradients. Our training algorithm provides a strong defense against various types of attacks. It can effectively counter these attacks while still achieving, while ensuring the model can generalize well as supported by our theoretical analysis. Importantly, it is 6 times faster than the current state-of-the-art algorithm, making it an efficient and effective solution. We have a follow-up paper that builds on the previous paper and significantly enhances the efficiency of our approach. To address the issue of bias toward the majority in large real-world data sets, we balance the size of gradient clusters. This approach helps improve the model's performance on minority groups in the data. But balancing the size of gradient clusters in the bird example on the left, we enable the model to focus on learning the birds rather than background. As a result, we observe a significant improvement in accuracy for the minority groups, with an increase of 20 to 40%. We also fix vision language models trained on billions of image and text pairs. And here are the takeaways for my talk today. Thank you for your attention.
Thank you. All right. Ryan, come on. You will talk about AI models. I think. Language processing models, indeed. Okay.
So hi everyone, my name is Dain. I'm a third-year PhD student advised by Professor Kai-Wei Chang. So thanks for inviting me. And today my presentation topic is building generalizable and inclusive language processing models across tasks and user groups. So right now, with the development of AI techniques, so people expect AI models can provide various functionalities such as answering questions, common sense reasoning, and responding to humans fluently. And the diverse needs from users may require AI models to be more generalizable across different tasks. Also, as AI models become stronger and stronger, so the usage of AI techniques will be much broader across regions and genders. So AI should not only be applied in Western countries. It should also, we also want to see it can bring some equivalent benefits to user groups in other non-Western countries. So, and at the same time, so the AI techniques should be beneficial to all the gender groups. So overall, it's very important to make models become more inclusive across regions and genders, so as to benefit all the groups all over the world. But if we don't consider the model inclusivity of some current AI models, so we are just designing some AI applications for certain groups and ignoring a large proportion of all the other people around the world. So to this end, my research interest is building generalizable and inclusive language processing models across tasks and user groups. And right now I have several papers working on building inclusive models across both regions and gender groups. So, and then I will mainly take the geographical inclusivity as an example to demonstrate my research line. So, so as I mentioned before, we want to build a inclusive model across different regions. But if we really consider the geographical inclusivity, so what should we watch out for? And actually, we find that the knowledge is actually geographically diverse, or we can call it geodiverse. And then I will take some wedding examples to illustrate my idea. So we may directly think of the wedding scenes like the three pictures below. So the bride will wear a white dress and the groom will wear a black suit. But the question is, do all the weddings look like this? So the answer is no. So so this page shows some other wedding scenarios in other regions. So for example, in traditional Chinese weddings, so the bride will be wearing red and their faces are covered with red clothes. So this means that the common sense knowledge about Western weddings doesn't apply for all the other weddings in non-Western countries. So, so we first try to evaluate the geographical inclusivity of the existing pre-trained language models. And so in my first paper, GDVCR, so we try to focus on how much the performance gap over Western and non-Western data is. And in my second paper, GeoMNAMA, so we want to use some knowledge probing method to figure out if multilingual pre-trained language models can really learn the geodiverse knowledge well or not. And from both papers, we find that the current pre-trained models are still far away from being inclusive. And beyond evaluation, we also design some methods to improve the model inclusivity. And in my geo paper, so we try to leverage the attributes of some geodiverse visual concepts and design some pre-training objectives to help the model to learn better geodiverse knowledge. And we finally find that the GEVO achieves total performance, and also the performance will be more balanced on some geodiverse vision and language tasks. And also it becomes competitive on some common vision and language tasks. And also we apply some causal inference and ethical intervention methods to produce more balanced predictions and generations. And yeah, so for my short-term goal, so I want to explore more on build models generalizable across different tasks with some instruction tuning methods. And also I want to explore how to make the current large language models to learn some low resource language for broader usage. Yeah, that's it.
Thank you very much. Okay, now I saved the talk about the most important, exciting, etc. topic for the end. At least that's what I think. Shixing, come on. Last talk of the day.
Yes.
More machine learning, but this time it doesn't have probabilistic stuff in there.
Right.
Yeah, please.
Okay. Hi all, I'm Jill. I'm a PhD student advised by Professor Guy van den Broek. And today I'll talk about my work on learning and probabilistic inference with constraints and its applications. So constraints always arise in real world. So for example, charge need to be neutral in chemistry, and also constraints can come from poorly annotated data, model sparsity constraints, or domain knowledge. How to deal with these constraints is out of the reach of most existing models. Some of them attempt to do ad hoc approximation to the probability of these constraints, while such probabilities are actually tractable, as shown by some of our recent work. So the goal of my research is to enable machine learning models to perform learning and inference under such constraints. And next, I will introduce some of my recent work towards this goal. So in current machine learning, when people train their models to make predictions, what they do is that they will take the model that achieves the lowest loss as their final model. However, if you look at the loss surface as shown here, you can see that there could be infinitely many model parameters that all give you models with low loss. Another question is, what is a good way to aggregate all these good models to make a reliable prediction? And the solution that Bayesian deep learning gives is to marginalize over all the parameter, or marginalize over the predictions over the parameter space or weight space. But the marginal computation, as shown here, requires to integrate over predictions. And these predictions are possibly from a neural network with non-linearity, such as ReLU. And to tackle this issue, we propose to apply a probabilistic inference framework called weighted model integration that allows to do efficient inference in the presence of arithmetic constraints. And we find that our proposed solution can indeed help deliver better predictions as well as more accurate uncertainty estimation. And another scenario where we need to deal with constraint is when we would like to model a distribution of subsets of a fixed subset size. An example application of the subset distribution is called learning to explain. So in this task, given a review for beer as a piece of text, the goal is to take exactly 10 words from this text, from this review, to get rid of the redundant information, and then give this subset to a model to predict the taste score for the beer. And to solve this task, we propose to leverage the probability of the exactly k constraint to update the parameters in the model. And in this way, the model is able to learn which 10 words are more likely to help make good predictions. And our proposed gradient estimator shows significantly lower bias and also lower variance than all other existing estimators, and predicts well in practice. And another recent work that I have done recently is about weakly supervised learning. So the goal here is to train our classifiers under weak supervision. In classical supervised learning setting, each instance in the training dataset has its own label. However, in weakly supervised setting, the supervision information is weak. So for example, in the learning from label proportion setting and also in the setting of multiple instance learning, the training instances are grouped into bags, and the supervision is given at the bag level instead of instance level. And in some other setting, only a partial of positive instances are labeled. And we find out that all this weak supervision information can actually be encoded into constraints on label counts. And we propose to train the classifiers based on the probability of these count constraints. And this proposed approach is able to outperform the existing baselines on these different settings, and they're able to train a better classifiers, even in the presence of just weak supervision. So some of my ongoing and future work is to build machine learning models that can deal with complicated constraints and deliver accurate and efficient inference. Also, I'm interested in applying some of our developed algorithms to other fields, such as computational chemistry, for example, in the application of meta-organic frameworks, where they have discharge neutral constraints. And that's all. Thanks for your time.
Okay, all right.
I think I just want to say thank you all for coming. Thanks to all the speakers. Thanks to Amazon for supporting our students. And I hope you can get home safely without being drowning in the rain.